This is 1.5 Part B. We're talking about solving quadratic equations. In Part A, we looked at the factoring method. In Part B, we're going to look at a new method, the square root method. The overall idea here is that if we know the square of some number is equal to n, then x itself must be plus or minus the square root of n. To think about that for just a moment, think about this x squared equals n again. All we're really doing is taking the square root on both sides of the equation. Right? You know, you could do something to an equation as long as you do the same thing on both sides. Square root of x squared would be x. And on this side, I would get the square root of n. Now, the only problem with this is the fact that, technically speaking, there are two numbers that are truly square roots of any positive number. Think for a moment about the perfect square 25. 5 squared is 25, but negative 5 squared is also 25. In order to not lose that possibility that the square root was actually negative, whenever we put a square root into an equation, we always put plus or minus with it. That way we don't lose the negative solution. All right, in order to use the square root method effectively, we will need to know just a little bit about simplifying radicals. Once we get the square root, how do we write that final answer if it doesn't come out evenly? So in the context of practicing our square root method, at least the simpler forms, we're also going to learn a bit about simplifying radicals. The first little rule for simplifying radicals is that we always have to remove any factor that's a perfect square from under the radical. Here's what I mean by that. In Part A, I would want to start, just like we said, by taking the square root on both sides, making sure to include both the positive and negative square roots. On the left, the square root of x squared is just x. Now on the right, the square root of 75 doesn't come out evenly, but I do know that there's a perfect square that goes evenly into 75, namely 25. If perfect squares are not something that you just sort of have in your head, you might consider just writing yourself out a quick list of perfect squares. It doesn't take very much time. This is something you could even do like in the margin on a test or something like that, if it helps you to have it handy. And by having that nearby, it might help you when you're trying to break down these radicals. So I'm looking at 75, and I'm running through it, and I'm saying, which of these perfect squares goes evenly into 75? And of course, the 25 does. It's 25 times 3. So I'm going to break apart my radical as the square root of 25 times the square root of 3. And then I can say the square root of 25 really is just 5. The square root of 3 doesn't come out evenly, so I'll just leave it as the square root of 3. And there are my two solutions. Positive 5 square root 3 and negative 5 square root 3. By the way, just to prove to yourself that we haven't done anything strange here in simplifying this, if I were to grab my calculator for a moment and take the square root of 75, I get about 8.66 something. Now take 5 times the square root of 3. And notice that we get exactly the same value. This is just what we consider a simplified form of that. It's kind of the radical equivalent of reducing a fraction to lowest terms or something like that. We call it the simplest radical form. One other thing I should probably mention is for convenience, when we're writing these things, we often use the plus or minus notation to show the two solutions. But just fair warning, when you enter your answers into the computer, it usually requires that you write them separately. So you'll have to put in 5 square root 3, comma, negative 5 square root 3 to get the two solutions into MyMathLab. All right, let's try B. Once again, I'm going to start by saying I have the x squared here. So let's get rid of the x squared by taking the square root. And of course, I have to do it on both sides. So I've got the square root of 180, which I'm pretty suspicious I can probably simplify if I break it apart. And this is one that I do want to mention. It's worth taking just a couple of minutes to try out a couple things on the calculator. Right away, for example, I might say, oh gosh, yeah, 9 definitely goes into 180. That'd be 9 times 20, right? But that's such a big number that I'm suspicious that there might be something even bigger that's going to work. It's to your advantage to use the biggest possible number that goes into that 180. So I know 9 works, but let's just check it out and see if anything else does. 16 did not. 25 did not. Whoops, that should have been 36. 36 does. 36 times 5. Again, it's to my advantage to use the biggest divisor I can, so I'm going to go with that one. 36 times 5. Square root of 36 is 6. And the square root of 5 I can't simplify, so I'll just leave it the way it is. Plus or minus 6 times the square root of 5 is what I'll end up getting. If you didn't happen to see that 36, I just want to show you what would have happened. I'm just going to grab a sheet of scrap paper here. Let's say that I had that plus or minus the square root of 180. And I had happened to see that 9 goes in first. And so I went ahead and used 9 times 20. The square root of 9 is 3. But then I'm looking at that square root of 20 thinking, wait a minute, there's still a perfect square that goes in there evenly. 4. So I'd have to break it down again. Square root of 4, square root of 5. So I have plus or minus 3 times. Now the square root of 4 is 2 times the square root of 5. And so notice I do end up with exactly the same final answer. 3 times 2 would give me the 6 square root 5. It just took me a little bit longer to get there. So that's why I was saying it's to your advantage to use the largest perfect square you can find that goes in evenly. But if you don't happen to notice it, it's not as though you won't eventually be able to get there. You just might have to take an extra step. All right, so the second rule of simplifying radicals. First rule was remove radicals that are, or remove perfect square factors, rather. The second rule is rationalize denominators. We never leave a square root in the denominator. Sometimes that just happens naturally, like in letter A here. When I go ahead and do the same thing, I want to get rid of that square, so I'm going to take the square root. Now on the top, the square root of 5 doesn't come out evenly, so I'll just leave it as the square root of 5. But on the bottom, the square root of 16, that's 4, which is great, because there's no longer any radicals, any square roots left in my denominator. And so I can leave this as my final answer. Other times it just doesn't happen that nicely for me. So let's take a look at B. I'm going to start the same way. I take the square root on both sides. Don't forget my plus or minus. And the top, I've got the square root of 7. On the bottom, I'm going to have a square root of 6. That did not come out evenly. What I want to do is ask myself, what's the smallest number I could multiply 6 by to turn it into one of these perfect squares so that I could take the square root and have it come out evenly? Well, I know 6 times 6 gives me the 36, so that's what I'm going to do. I'm going to multiply by the square root of 6, top and bottom. Just a reminder, why is it that we have to multiply by both the top and the bottom? What I'm really doing is multiplying by a fraction that's equivalent to 1, right? Square root of 6 over square root of 6 is the same as 1. And multiplying by 1 doesn't change the value of my fraction. It's going to change the appearance, but I haven't changed the value. All right, so I have plus or minus. On the top, I would have the square root of 42. On the bottom, I have the square root of 36, which is just 6. And there's my solution. All right, one more thing about simplifying square roots before we run through some more general quadratic equations. What happens when you take the square root, but you have a negative number under your square root? When that happens, what we have is an imaginary number, and we use the fact that the square root of -1 is called I, the imaginary unit, to remove the negative from underneath the radical. So that's kind of our third simplifying fact for square roots. So in the next example, if I have x squared equals -40, I'll once again start by taking the square root on both sides, remembering the plus or minus in front of my radical. And what I'm going to do here is I'm going to break down that -40. And since it's a negative number, I'm going to say right away, let's just get rid of the negative under the radical by writing it as the square root of -1 times some more stuff, of course. That square root of -1 I'll be writing as an I in my next step. All right, what about the square root of 40? Well, the perfect square 4 goes into that, so I'll break that down as the square root of 4 times the square root of 10. Again, this square root of -1 is I, the imaginary unit, multiplied by the square root of 4, which is 2, times the square root of 10. Usually when we write these things, we have kind of a preferred order to write them in. Typically, instead of I times 2, we like to write it as 2I square root 10. But we do prefer to keep the I in front of the square root so it doesn't start sneaking and looking like it's underneath the radical, which it's not. So the imaginary numbers, 2I square root 10 and -2I square root 10, are our solutions. Let's try a similar approach to B. Need a little more space here, so let me start up here. I'm going to start again by taking the square root of both sides. So on the top, I would have the square root of -1 times the square root of 3. Or in other words, that's going to turn into an I times the square root of 3. I'll do that in my next step, although as you get comfortable, if you want to skip that little step of writing the square root of -1 and just bringing that negative out as an I, you can certainly do that. Now the bottom unfortunately does not come out evenly, so I'm going to be stuck with the square root of 8 there. We know we can't leave a radical in the denominator. So once again, I'm going to ask myself, what would I have to multiply that 8 by to turn it into a perfect square? The smallest number that would work is actually 2. 8 times 2 would give me 16, and that comes out evenly. So let's multiply by the square root of 2. Again, top and bottom, I'm really just multiplying by a form of 1. So let's see, square root of negative 1, that's I. Square root 3 times square root 2 is square root 6. And the bottom, square root 16, which is really just 4. All right, so we're going to use these skills in some slightly more involved quadratic equation solving in the next segment of this video.